The track on a railway or railroad, also known as the permanent way, is the structure consisting of the rails, fasteners, railroad ties and ballast plus the underlying subgrade. It enables trains to move by providing a dependable surface for the wheels to roll. For clarity, it is often referred to as railway track or railroad track. Tracks where electric trains or electric trams run are equipped with an electrification system such as an overhead electrical power line or an additional electrified rail. The term permanent way also refers to the track in addition to line-side structures such as fences etc. Structure. Traditional track structure notwithstanding modern technical developments, the overwhelmingly dominant track form worldwide consists of flat-bottom steel rails supported on timber pre-stressed concrete sleepers, which are themselves laid on crushed stone ballast. Most railroads with heavy traffic use continuously welded rails supported by sleepers attached via base plates that spread the load. A plastic or rubber pad is usually placed between the rail and the tie plate where concrete sleepers are used. The rail is usually held down to the sleeper with resilient fastenings, although cut spikes are widely used in North American practice. For much of the 20th century, rail track used softwood timber sleepers and jointed rails, and a considerable extent of this track type remains on secondary and tertiary routes. The rails were typically of flat-bottom section fastened to the sleepers with dog spikes through a flat tie plate in North America and Australia, and typically of bullhead section carried in cast-iron chairs in British and Irish practice. The London, Midland and Scottish Railway pioneered the change to flat-bottomed rail and the supposed advantage of bullhead rail, that the rail could be turned over and reused when the top surface had become worn, turned out to be unworkable in practice because the underside was usually ruined by fretting. For the chairs, jointed rails were used at first because the technology did not offer any alternative. However, the intrinsic weakness in resisting vertical loading results in the ballast becoming depressed and a heavy maintenance workload is imposed to prevent unacceptable geometrical defects at the joints. The joints also needed to be lubricated, and wear at the fishplate mating surfaces needed to be rectified by shimming. For this reason, jointed track is not financially appropriate for heavily operated railroads. Timber sleepers are of many available timbers, and are often treated with creosote, copper chrome arsenic, or other wood preservative. Pre-stressed concrete sleepers are often used where timber is scarce and where tonnage speeds are high. Steel is used in some applications. The track ballast is customarily crushed stone, and the purpose of this is to support the sleepers and allow some adjustment of the position, while allowing free drainage. Ballastless track. A disadvantage of traditional track structures is the heavy demand for maintenance, particularly surfacing and lining to restore the desired track geometry and smoothness of vehicle running. Weakness of the subgrade and drainage deficiencies also lead to heavy maintenance costs. This can be overcome by using ballastless track. In its simplest form, this consists of a continuous slab of concrete with the rails supported directly on its upper surface. There are a number of proprietary systems, and variations include a continuous reinforced concrete slab, or alternatively the use of precast pre-stressed concrete units laid on a base layer. Many permutations of design have been put forward. However, ballastless track has a high initial cost, and in the case of existing railroads, the upgrade to such requires closure of the route for a long period. Its whole life cost can be lower because of the reduction in maintenance. Ballastless track is usually considered for new very high speed or very high loading routes in short extensions that require additional strength. length, or for localized replacement where there are exceptional maintenance difficulties, for example in tunnels. Ladder track utilizes sleepers aligned along the same direction as the rails with rung-like gauge restraining cross members. Both ballasted and ballastless types exist. Continuous longitudinally supported track. Early railways experimented with continuous bearing rail track, in which the rail was supported along its length, with examples including Brunel's Bork Road on the Great Western Railway, as well as use on the Newcastle and North Shields Railway. On the Lancashire and Yorkshire Railway tour designed by John Hawkshaw, and elsewhere, continuous bearing designs were also promoted by other engineers. The system was trialled on the Baltimore and Ohio Railway in the 1840s, but was found to be more expensive to maintain than rail with cross sleepers. Later applications of continuously supported track include ballast-For Beatty's embedded slab track, which uses a rounded rectangular rail profile embedded in a slip-formed concrete base. The embedded rail structure, used in the Netherlands since 1976, initially used a conventional UIC-54 rail embedded in concrete, and later developed to use a mushroom-shaped SA-42 rail profile, a version for light rail using a rail supported in an asphalt concrete fill. Steel trough has also been developed. Historical development. The technology of rail tracks developed over a long period, starting with primitive timber rails in mines in the 17th century. Modern track typically uses hot-rolled steel with a profile of an asymmetrical rounded I-beam. Unlike some other uses of iron and steel, railway rails are subject to very high stresses and have to be made of very high-quality steel alloy. It took many decades to improve the quality of the materials, including the change from iron to steel. The stronger the rails and the rest of the trackwork, the heavier and faster the trains the track can carry. Other profiles of rail include bullhead rail, grooved rail, flat-bottomed rail, and grooved rail. North American railroads until the mid to late 20th century used rails 39 feet long so they could be carried in gondola cars, often 40 feet long. As gondola sizes increased, so did rail lengths. According to the Railway Gazette, the 150 km rail line being built for the Baffin Inland Iron Mine on Baffin Island will use older carbon steel alloys for its rails, instead of more modern, higher-performance alloys, because modern alloy rails can become brittle at very low temperatures. Wooden rails. The earliest rails were made of wood, which wore out quickly. Hardwood such as jarrah and karri were better than softwood such as fir. Longitudinal sleepers such as Brunel's Bork Road are topped with iron or steel rails that are lighter than they then might otherwise be because of the support of the sleepers. Rail classification. Rail is graded by weight over a standard length. Heavier rail can support greater axle loads and higher train speeds without sustaining damage than lighter rail, but at a greater cost. In North America and the United Kingdom, rail is graded by its linear density in pounds per yard, so 130-pound rail would weigh 130 pounds. YD. The usual range is 115 to 141 pounds. YD. In Europe, rail is graded in kilograms per meter and the usual range is 40 to 60 kilograms per meter. The heaviest rail mass produced was 155 pounds per yard and was rolled for the Pennsylvania Railroad. The United Kingdom is in the process of transition from the imperial to metric rating of rail. Joining rails. Rails are produced in fixed lengths and need to be joined end-to-end to make a continuous surface on which trains may run. The traditional method of joining the rails is to bolt them together using metal fish plates, producing jointed track. For more modern usage, particularly where higher speeds are required, the lengths of rail may be welded together to form continuous welded rail. Jointed track is made using lengths of rail, usually around 20 meters long and 39 or 78 feet long, bolted together using perforated steel plates known as fish plates or joint bars. Fish plates are usually 600 mm long, used in pairs either side of the rail ends and bolted together. The bolts may be oppositely oriented so that in the event of a derailment and a wheel flange striking the joint, only some of the bolts will be sheared, reducing the likelihood of the rails misaligning with each other and exacerbating the seriousness of the derailment. This technique is not applied universally, European practice being to have all the bolt heads on the same side of the rail. Small gaps which function as expansion joints are deliberately left between the rail ends to allow for expansion of the rails in hot weather. European practice was to have the rail joints on both rails adjacent to each other, while North American practice is to stagger them. Because of the small gaps left between the rails, when trains pass over jointed tracks they make a clickety-clack sound. Unless it is well maintained, jointed track does not have the right quality of welded rail and is less desirable for high-speed trains. However, jointed track is still used in many countries on lower speed lines and sidings, and is used extensively in poorer countries due to the lower construction cost and the simpler equipment required for its installation and maintenance. A major problem of jointed track is cracking around the bolt holes, which can lead to breaking of the rail head. This was the cause of the Hither Green rail crash, which caused British Railways to begin converting much of its track to continuous welded rail. Insulated joints where track circuits exist for signaling purposes, insulated block joints are required. These compound the weaknesses of ordinary joints. Specially made glued joints, where all the gaps are filled with epoxy resin, increase the strength again. As an alternative to the insulated joint, audio frequency track circuits can be employed using a tuned loop formed in approximately 20 meters of the rail as part of the blocking circuit. Some insulated joints are unavoidable within turnouts. Another alternative is the axle counter, which can reduce the number of track circuits and thus the number of insulated rail joints required. Continuous welded rail. Most modern railways use continuous welded rail, sometimes referred to as ribbon rails. In this form of track, the rails are welded together by utilizing flash butt welding to form one continuous rail that may be several kilometers long. Because there are few joints, this form of track is very strong, gives a smooth ride, and needs less maintenance. Trains can travel on it at higher speeds and with less friction. Welded rails are more expensive to lay than jointed tracks, but have much lower maintenance costs. The first welded track was used in Germany in 1924 and the US in 1930 and has become common on main lines since the 1950s. The preferred process of flash butt welding involves an automated track laying machine running a strong electrical current through the touching ends of two unjoined pieces of rail. The ends become white-hot due to electrical resistance and then pressed together, forming a strong weld. Thermite welding is used to repair or splice together existing CWR segments. This is a manual process requiring a reaction crucible and form to contain the molten iron. Thermite bonded joints are seen as less reliable and more prone to fracture or break. If not restrained, rails would lengthen in hot weather and shrink in cold weather. To provide this restraint, the rail is prevented from moving in relation to the sleeper by use of clips or anchors. Attention needs to be paid to compacting the ballast effectively, including under, between, and at the ends of the sleepers, to prevent the sleepers from moving. Anchors are more common for wooden sleepers, whereas most concrete or steel sleepers are fastened to the rail by special clips that resist longitudinal movement of the rail. There is no theoretical limit to how long a welded rail can be. However, if longitudinal and lateral restraint are insufficient, the truck could become distorted in hot weather and cause a derailment. Distortion due to heat expansion is known in North America as sun kink, and elsewhere as buckling. In extreme hot weather, special inspections are required to monitor sections of track known to be problematic. After new segments of rail are laid, or defective rails replaced, the rails can be artificially stressed if the temperature of the rail during laying is cooler than what is desired. The stressing process involves either heating the rails, causing them to expand, or stretching the rails with hydraulic equipment. They are then fastened to the sleepers in their expanded form. This process ensures that the rail will not expand much further in subsequent hot weather. In cold weather, the rails try to contract, but because they are firmly fastened, cannot do so. In effect, stressed rails are a bit like a piece of stretched elastic firmly fastened down. CWR rail is laid at a temperature roughly midway between the extremes experienced at that location. This installation procedure is intended to prevent tracks from buckling in summer heat or pulling apart in winter cold. In North America, because broken rails are typically detected by interruption of the current in the signaling system, they are seen as less of a potential hazard than undetected heat kinks. Joints are used in continuous welded rail when necessary, usually for signal circuit gaps. Instead of a joint that passes straight across the rail, the two rail ends are sometimes cut at an angle to give a smoother transition. In extreme cases, such as at the end of long bridges, a breather switch gives a smooth path for the wheels while allowing the end of one rail to expand relative to the next rail. Sleepers. A sleeper is a rectangular object on which the rails are supported and fixed. The sleeper has two main roles: to transfer the loads from the rails to the track ballast and the ground underneath, and to hold the rails to the correct width apart. They are generally laid transversely to the rails. Fixing rails to sleepers. Various methods exist for fixing the rail to the sleeper. Historically, spikes gave way to cast iron chairs fixed to the sleeper. More recently, springs are used to fix the rail to the sleeper chair. Portable track. Sometimes rail tracks are designed to be portable and moved from one place to another as required. During construction of the Panama Canal, tracks were moved around excavation works. These tracks were 5 feet and the rolling stock full size. Portable tracks have often been used in open pit mines. Cane railways often had permanent tracks for the main lines, with portable tracks serving the cane fields themselves. These tracks were narrow gauge, and the portable track came in straights, curves, and turnouts, rather like on a model railway. Decoval was a source of many portable light rail tracks, also used for military purposes. The permanent way is called because temporary way tracks were often used in the construction of the permanent way. Layout. The geometry of the tracks is three-dimensional by nature, but the standards that express the speed limits and other regulations in the areas of track gauge, alignment, elevation, curvature and track surface are usually expressed in two separate layouts for horizontal and vertical. Horizontal layout is the track layout on the horizontal plane. This involves the layout of three main track types: tangent track, curved track, and track transition curve, which connects between a tangent and a curved track. Vertical layout is the track layout on the vertical plane, including the concepts such as cross-level, cant and gradient. Gauge. During the early days of rail, there was considerable variation in the gauge used by different systems. Today, 54.8% of the the world's railways use a gauge of 1,435 mm, known as standard or international gauge. Gauges wider than standard gauge are called broad gauge, narrower narrow gauge. Some stretches of track are dual gauge, with 3 parallel rails in place of the usual 2, to allow trains of 2 different gauges to use the same track. Gauge can safely vary over a range. For example, U.S. federal safety standards allow standard gauge to vary from 4 feet 8 into 4 feet 9.5 in for operation up to 60 miles per hour. Maintenance. Track needs regular maintenance to remain in good order, especially when high-speed trains are involved. Inadequate maintenance may lead to slow order being imposed to avoid accidents. Track maintenance was at one time hard manual labor, requiring teams of laborers, or trackmen, who used lining bars to correct irregularities in horizontal alignment of the track, and tamping and jacks to correct vertical irregularities. Currently, maintenance is facilitated by a variety of specialized machines. The surface of the head of each of the 2 rails can be maintained by using a rail grinder. Common maintenance jobs include changing sleepers, lubricating and adjusting switches, tightening loose track components, and surfacing and lining track to keep straight sections straight and curves within maintenance limits. The process of sleeper and rail replacement can be automated by using a track renewal train, spraying ballast with herbicide to prevent weeds growing through, and redistributing the ballast is typically done with a special weed-killing train. Over time, ballast is crushed and moved by the weight of trains passing over it, periodically requiring releveling and eventually to be cleaned or replaced. If this is not done, the tracks may become uneven, causing swaying, rough riding and possibly derailments. An alternative to tamping is to lift the rails and sleepers and reinsert the ballast beneath. For this, specialist stone blower trains are used. Rail inspections utilize non-destructive testing methods to detect internal flaws in the rails. This is done by using specially equipped rail trucks, inspection cars, or in some cases handheld inspection devices. Rails must be replaced before the railhead profile wears to a degree that may trigger a derailment. Worn mainline rails usually have sufficient life remaining to be used on a branch line, siding a stub afterwards, and are cascaded to those applications. The environmental conditions along railroad track create a unique railway ecosystem. This is particularly so in the United Kingdom, where steam locomotives are only used on special services and vegetation has not been trimmed back so thoroughly. This creates a fire risk in prolonged dry weather. In the UK, the cess is used by track repair crews to walk to a worksite, and as a safe place to stand when a train is passing. This helps when doing minor work, while needing to keep trains running, by not needing the high railer transport vehicle blocking the line to transport crew to get to the site. Bed and foundation. Railway tracks are generally laid on a bed of stone. Track ballast, a track bed, in turn, is supported by prepared earthworks known as the track formation. The formation comprises the subgrade and a layer of sand or stone dust, known as the blanket, which restricts the upward migration of wet clay or silt. There may also be layers of waterproof fabric to prevent water penetrating to the subgrade. The track and ballast form the permanent way. The term foundation may be used to refer to the ballast and formation, i.e. all man-made structures below the tracks. Additional measures are required where the track is laid over permafrost, such as on the Chingsang Railway in Tibet. For example, transverse pipes through the subgrade allow cold air to penetrate the formation and prevent that subgrade from melting. The subgrade layers are slightly sloped to one side to help drainage of water. Rubber sheets may be inserted to help drainage and also also protect iron bridgework from being affected by rust. Bibliography. Pike, J. Track, Sutton Publishing, ISBN 0-7509-26929. Ziran, Emanesdorf, O. Simulation of the dynamic behavior of bedding foundation soil in the time domain, Springer Verlag. Robinson, A.M. Fatigue in Railway Infrastructure. Woodhead Publishing Limited. ISBN 978-185573-740-2. Lewis, R. Wheel, Rail Interface Handbook. Woodhead Publishing Limited. ISBN 978184569-428.